Hello everyone, this is Professor Iris Miano with your Day 25 lecture video concerning sections 9.2 and 9.3, which cover the parabola and the ellipse. So parabolas we've already discussed at some length, the upward and downward facing parabolas, but now we're going to throw into the mix left and right facing parabolas, and so we need a little bit more information in order to throw those two other types of parabolas into our repertoire, and that's going to come in into the form of the focus and directrix. As you can see with my GIF that I've included in the lecture notes, these two elements give us some positioning information, because for any parabola, its focus and directrix are equidistant from any point on the parabola. So as you can see with this point P moving up and down the trajectory of the blue parabola, the distance from P to the focus, which is the blue dot above the vertex, they're both blue, but the one that's floating above the vertex, and the directrix line are all equidistant at any point from any point P on the parabola. Okay, so if you are interested in using this GIF for your own purposes, you can click off the hyperlink here. Our parabola now will be more or less re-represented using this format here, where we'll have either x or y squared, and it'll be equal to 4 times some unknown value a, which will help us figure out where our focus is in our directrix line. A is always going to be positive. And depending on if we have left or right facing parabolas, that's the B and A subfigures for figure 7 respectively, we're going to have the y values squared for those parabola equations. X will be squared if we have regular run-of-the-mill upward and downward facing parabolas, as you can see in figure 7C and D respectively. Now, if the factor of 4 is going to be positive or negative, that'll be determined if we have an upward or downward for positive and negative x squared parabolas. If we have a y squared parabola, if the 4 is positive, then the parabola will be right facing, or if the 4 is negative, it'll be left facing. So you'll want to really get to know Table 1 because it's going to help you figure out the focus, point, directrix line, and equation depending on what type of information you're given. Either you're given a figure, or you're given an equation, or you're given the focus, directrix, or some other piece of information, maybe even the vertex. So Table 1 and Figure 7 are a summary of characteristic elements associated with parabolas that have their vertex at the origin. If you don't have your vertex at the origin, you're going to want to look at Table 2 and Figure 11, which you'll see if you scroll down. Okay, but before we get into that, I want to introduce another element to this, which I don't have formally defined on here for no particular reason, other than it has got to be the most unfortunate term I've ever encountered in my mathematical career, and that's going to be the lattice rectum. Yes, I just used the word rectum, and I'm not talking about an anatomical element to a person. I'm talking about the opening. Yes, they use the word opening to describe the definition of lattice rectum. It's the opening of the parabola. So basically, it's going to be the line parallel to the directrix but going through the focus. So if you're looking at my drawing here I guess I'll do it in green just to mix it up a little bit. That's going to be this line right here for point for figure A, right? So that's this line, but it's these 2 points are going to be the LR points. I'm going to call them LR for short now. So I'll draw the LR points for all of these figures. It's going to be where this horizontal line right here going through the focus intersects with the parabola itself. Those are your LRs. It's going to be horizontal if you have an opening up or opening down parabola. Yeah, so here's your LR points there. And they're just, it's more information that's going to help you draw your figure, okay? So those are your LR points. Great, we'll get into that a little bit more. So again, just to be clear, table 1, figure 7, these are things you'll want to keep in mind when trying to find the equation or graph or whatever you're being asked to do regarding parabolas that are centered or have their vertex rather at the origin. If your vertex is somewhere else besides the origin, you're going to want to focus on table 2, which is, you know, more complicated, but basically it's table 1, but with some horizontal and vertical transformations. And I want to highlight the textbook's note where they're like, hey, don't try and memorize this. Just, you know, get to know table 1 and make some adjustments via transformations that you already know how to do in the vertical and horizontal sense. Okay, so it's a lot of information to take in, but I do want to just get started on some exercises. And then the practice will hopefully help you absorb a lot of the information that's in these tables, okay? So the first set of exercises are numbers 13 through 20 in the textbook homework set, and they are graphs of parabolas, and we have just as many equations to match them up with. So we want to just look at the figure, be able to glean some information about what we think the parabola is doing, and that's going to help us be able to match it to its form. So looking first at number 13, you might notice that you have an upward facing parabola that has its vertex at the origin, okay? So upward facing means that it's going to be squared in x, and also have a positive 4 factor involved, and centered at the origin means it's not going to have any thing added or subtracted directly on the x's or the y's. So I'm looking at B here. B is going to be the equation that matches with number 13. Moving on to number 14, I am having my vertex at 1, 1. So I'll have x minus 1, y minus 1 inside of some parentheses with the form of the equation that I'm looking for because my h and my k are each 1. I know that I'm going to be squared in y, and I'm going to be having a -4 factor involved. So the one that fits all of that criteria is G right here. I'm squared in y, my h and my k values are each 1, and the factor of 4 is negative. So that'll be G. For number 15, I open to the right. Again, my vertex is at 1, 1. So opening to the right means I'm going to have a square in y rather than x, but facing to the right I'm going to have a +4 factor, and we're going to subtract 1 from y and x, so that's going to be e, right? Squaring in y, h and k are each 1, +4 factor. Number 16, I'm opening down, so that means a -4 factor and squaring in x, and my vertex is at 0, 0. So looking at all the options here, D is the best one. Squared in x, -4 factor, origin vertex. So again, that's D. For 17, I have a vertex at -1, -1. So it's going to be x plus 1, y plus 1 in the form of the equation of the line. My h and my k both being -1. I'm facing down, so my 4 factor is going to be negative, and I am squaring in x. So that'll be h, right? X is squared. It's a +1 for the x and the y, and the factor 4 is negative. That's h right there. For 18, I'm opening to the right, which means that I'm a y squared, and that my 4 factor is positive, and I am having my vertex at the origin. So it's looking like A is going to be the best fit there. A. Squared in y means I'm right facing, +4 coefficient, and no transformations with vertical or horizontal. Okay, so almost the same thing happening over here, but I'm going to be left facing, so that means I'm just like A, but I have a -4 factor involved, so that'll be looking like C. Squaring in y, -4 factor, no transformations for the vertex centered at the origin. Okay, process of elimination, but let's analyze it anyway. Our vertex is at -1, -1, so I'm going to be adding 1 to both my x and my y directly. I'm opening upwards, so my 4 factor is positive, and I am squaring in x, so that's got to be f right here. Squaring in x, +1 + 1, +4. Okay, so hopefully that overview is going to help us move forward with some smoothness in these next elements here. Okay, let's find the equation of the parabola described, and we're only going to be given the focus and the vertex. So I'm going to plop some things on the coordinate plane provided that are given to me, and then go from there. Okay, so the focus being at 0, 2, what does that look like? 0, 2, that'll be right here. Vertex there. Okay, and the directrix line has to be on the other side of the vertex, and it's going to be horizontal here. So this will be more or less my directrix line there. Furthermore, the fact that my focus was 0, 2, this 2 value actually gives me my A. Okay, so from here I can say I know A equals 2. Oh, excuse me. Let's see. Are you going to erase for me? There we go. 2. Takes 2 tries sometimes. There we go. Yeah, this is running a little bit slow. I'm going to have to do some updates on Word, I guess. And so we know that we are going to be having a upward facing parabola. So the structure will be x squared equals 4. Oops. Back. 4ay, and we just determined that a was a 2. So that means the equation of the parabola is going to be x squared equals 8y. They also want us to get the LR points. So that's when you have your y equals -2. Oh, excuse me, that's the directrix, -2. But the y value here at the focus is at 2, right? So you want to say to yourself, okay, if there is a horizontal line going through that focus, where would it intersect with this parabola? Okay, so basically you want to take this a value and plug it in for y, and then solve for x. So here, x squared equals 8 times 2, which is 16. Take the square root of both sides. That means x either equals -4 or +4. So your LR points are going to be at -4, 2, and 4, 2. So if I take away this right here, it'll reveal all those elements there. Yep, here's my focus. Here are my LR points of -4, 2, 4, 2. My vertex, and here's my directrix line. All right, and so the red trajectory here is just my very smooth, graphically imposed version of this equation of the line. Let's click it twice. All right, and I also want to box up my LRs as well. Cool, and that'll do it for number 22. Okay. Now let's try another example where we have a vertex again at 0, 0. All right, so I'll just kind of throw that on there. And the axis of symmetry is the x-axis. So this horizontal axis of symmetry is going to tell us where we can find an additional point. And we know that the parabola contains the point 2, 3. So that'll be this point right here. So that means it has to also contain, by virtue of this being an axis of symmetry, its counterpart on the other side of the axis of symmetry, which would be at 2, -3, right there. So, you know, we're going to see that we are almost having a pretty clear visual of a right-facing parabola. So it's right facing. And that'll tell us that we are looking at the form y squared equals 4ax. Again, I'm going straight to this form because I know the vertex is at the origin. Furthermore, we can use these this point and then the additional point of 2, -3 in order to find the value of a by basically plugging those in. So y is either plus or minus 3, yeah? We're squaring it, and then we'll get 4a times 2. Okay, so that'll be 9 here. 2 times 4 is 8a. So that means that a equals 9/8. Kind of a weird number, but not incorrect. And then we can from there say that the focus has to be at a comma 0, so 9/8, 0, and the directrix has to be at x equals -9/8. Okay, we know we have got to be a vertical line going through the focus and, what's the word I'm looking for? And intersecting with the parabola that we know is going to be shaped kind of like this in order to find the LRs, right? LRs, plural, there's 2 of them. So basically you can find this by plugging in your 9/8 value for x and then solving for y. So that'll be y squared equals, the a value being 9/8, we have yet to actually formally give the equation of the line, which is y squared equals 9/2 x. How did I get that? I plugged in my a value of 9/8 that I calculated here. 9/8 times 4 gives you 9/2. Okay, so that's the equation of the line. Okay, whatever, who cares? This thing is acting too wonky for me to actually be able to use that properly. So anyway, if you want to find the value of your LRs, you got to plug in 9/8 in for x. And that'll give you 2 y values. So here, that'll give you 81/16, which awesomely, it's 2 perfect square numbers. You take the square root of both sides and you'll get plus or minus 9/4. So that means your LRs are the ordered pairs, 9/8, 9/4, and 9/8, -9/4. So let's go ahead and reveal all of these things. Indeed. Okay, so here is your point 2,3 that was given to you. Here's 2, -3 that was surmised by virtue of recognizing the axis of symmetry that was given. Here's my vertex. Here is my focus right here, which is happening at 9/8, 0, so just a little bit more than x equals 1, right? 8/8 being the 1, and then a little bit the other side, a little bit less than 1, we get the directrix line here in green. Okay, great. I think that just about covers everything. Oh, and our LRs are given right here and there. Go ahead and box those up too. Great. Moving on. Okay, let's graph another one, and this time we're given the focus at -4, 4, which is here. And the directrix line is y equals -2, which is looking like this, something like that. Here's my rough drawing. So I can tell from this bit of information that this right here has to be the location of my vertex. How do I know that? Because it's always splitting the difference between the focus and the directrix line as far as the vertex is concerned. You can just draw the vertical line, that passes through the focus and go halfway between the directrix and the focus, and you've got your vertex. Okay, so we know vertex is the ordered pair, -4, 1. So that gives you your h and your k values. Okay, furthermore, my y value, or excuse me, my y equals -2 directrix line that I have labeled right here, that has to come in the form of k minus a, right? So -2 therefore equals k minus a. Well, I just found that k was a 1, so -2 equals 1 minus a. That means a has to equal 3. So that gives me a lot of information. Do I have enough information to get the equation of the line? Well, sure I do, as long as I know that I have an upward facing parabola, which I know I have to have by virtue of the focus being on top and the directrix being a horizontal line down below. Okay, so I'm looking at x minus h quantity squared equals 4 positive 4a y minus k, and then it's basically a plug and chug game after that. X minus plus 4, because it was a -4 was the value of h, plus 4 squared equals 4 times a is 3, so that'll be 12 times the quantity y minus 1. So that's the equation of your line. Definitely box that up, you're going to need that. And then we're going to graph it. So it might be helpful, and they also want us to get the LRs. Now, the LRs happen when you have your focus y value, which is a 1, excuse me, or the, a y value is going to be, hold on another second. Oh, sorry, the focus y value is 4. I got myself a little confused there. Okay, so you're going to plug that in to your equation and solve for the 2 possible x values. So that'll be x plus 4 quantity squared equals 12 times the quantity 4 minus 1. 4 minus 1 gives you a 3. 3 times 12 is 36. Then we're dealing with this right here. Let's take the square root of both sides, and you'll get that x plus 4 is equal to plus or minus 6. So that means x can either equal -10 or 2. So therefore your LRs are the ordered pairs -10, 4, or 2, 4. So I can plot those, and that'll help draw what's going on here. Here's -10 up to 4. It's going to go through that point, and 2, 4. It's going to go through that point as well. You'll see that once I take off this cover, yep, that all those elements are in play. All right, very good. So again, start at the vertex, use the vertical, in this case, line of symmetry that you know has to happen, plot those LR points, and that'll help you figure out the width of the curve, the width of the opening, ew, gross, for your parabola. And yeah, and there you have it. Okay, let's do 2 more in this section, and then we're going to talk about ellipses. Okay, so in the next one, we are given the equation of the line, and it's our job to find the vertex, focus, the directrix, and to graph the parabola. So right off the bat from the structure, we can tell that the vertex happens at -1, 2, because the h value is 1 and the k value is, or sorry, h is -1, my bad. H is -1, and the k value is, oh, and I have them mixed up. Whoops, whoopsie doodle. Hold on. Let me correct this. H is associated with the value that's subtracted off the x. So yes, h is going to be 2. Oh boy. Let's see, is this catching up with me here? H equals 2, and then therefore the k value is -1. Okay. Furthermore, the fact that we don't have anything in this multiplier area other than -4, we know that that means that a has to equal just a 1. It's like the invisible factor there. And that alone allows us to get everything that we need, because the focus is h minus a, comma k. And where am I getting this from in the chart? Well, you might notice that since we have a -4 factor and we're squaring in y, that means that we're going to open to the left. So take that row of information from table 2 and you'll be able to get all of these values. So pairing that with the things that you've already taken from your chart here, you will get your focus of 1, -1. Your directrix line, I'll just call that D for short, is going to be x equals h plus a. So specifically here it'll be x equals 3 because h is 2 and a is 1. Furthermore, if you want to get a little bit more specific about, okay, so plotting these things, we have 1, -1 right here. As the focus, the directrix line is x equals 3. That'll be 1, 2, 3, this vertical line here. And the vertex will be at 2, -1. Okay, so here's the vertex. And so you know you're going to be opening this way, right? Okay, but you might be noticing that you will want to maybe know where you're going to cross the x-axis and cross the y-axis. So you can use what you know about basic y and x-intercept acquiring tools that you already have at your disposal in order to do that. So for the x-intercept, that's the easier one. You'll just set the y equal to 0. So you'll get 1 equals -4 times x minus 2. You'll divide both sides by -4, so you get -1/4 equals x minus 2. You'll add 2 to both sides and you'll get x equals 7/4. So that'll be, oh sorry, your x-intercept. Let's see, this is going to let me erase that. There we go. Hold on. I don't trust that it's, okay, there we go. And then you could do the same thing. So I'm just talking about getting the x-intercept and then the y-intercepts. You do something similar where you would set the y equal to, or the x equal to 0 rather, and that'll give you y plus 1 quantity squared equal to 8, right? So you'll take the square root of both sides and it'll be y equals plus or minus square root of 8 minus 1, or a -1 plus or minus that. Okay, so that'll give you some numbers. It'll be at 1.828 ... and then -3.828 ... Okay, so anyway, we have some values here. Let's go ahead and strip this away and show that, yeah, we have all the elements that we want. Anyway, so here is what 7/4 looks like, right there, the x-intercept, and the y-intercepts are at, again, 1.82. That's really close to 2, right? And then really close to -4. So it all evens out with this x and y intercept stuff. And then the rest of the stuff we just got from analyzing the equation. Okay, cool, moving on. Now let's wrap things up with just given a figure can we come up with the equation of this parabola? Sure enough. Okay, you'll notice a few things. The vertex is at 1, 0. So that's your h and your k values right there. We have an additional point at 0, 1. And it also happens to be the y-intercept. And we know, even though it's not explicitly shown, because we see that there's a symmetry in the x-axis, that it also has the point 0, -1. Okay. Furthermore, it opens to the left, so we know we have y minus k squared equals -4a times x minus h as the structure. And then as far as being able to solve for a is concerned, we're going to need to use one of the points in order to do that. So go ahead and plug in your h and your k, at least that you know. So that'll be y minus 0 squared equals -4a times x minus 1. And then, so this will just be y squared. Oh, sorry, we got to do that. Okay, so that's, we also need to, sorry, plug in, oh no, I want that, totally want that, sure. Y squared is -4a x minus 1. So, but you've got to plug in one of these points in order to get the rest of it. So let's go ahead and plug in this 0, 1. So we get 1 equals, and this all, this 0 is at the x, so we get -4a times the -1. So that'll be a equals 1/4. Cute. Okay, so all right, plugging that back into this equation here, we get y squared equals negative quantity x minus 1. Cute, and that's done. That's that. Okay. Whew. So again, just to be clear, we got from the figure the vertex that gave us our h and our k. We noticed that because of the direction it was facing, what the structure of the equation needed to look like, and then it was just a matter of using the additional point that they give us of 0, 1 in order to solve for a, plug that in again to the structure of the equation that we know based on the direction that the parabola is opening up, and Bob's your uncle. You have your equation, and we are ready to move on to ellipses. Okay. So just like I had a GIF for parabolas, I have another one for ellipses, and I made this one markedly smaller for no particular reason. If you like this GIF, you can go ahead and put it there, which is just to say that it's a collection of points whose sum from two foci, right, that's the plural of focus, are summed to be the same distance. So as you see in this figure here, as we move around the outer edge of this ellipse, we have two distances, blue and red, respectively, of between the point that's moving and the two foci. And if you add those two distances together, it is constant throughout. So that's the definition of an ellipse as we see it. There are some structures that are given to us. Either we have wide ellipses, so I usually call this one wide and this one tall. That's how I usually distinguish between these two. That'll determine the denominator's relative sizes. So when you have a wide ellipse, the larger denominator is underneath the x squared term. And if you have a taller ellipse, the larger denominator is underneath the y squared term. And the structure that we use in order to go from graph to equation and back again always has the square of x over some value plus the square of y over some other squared value equal to 1. So having it equal to 1 is very important to the structure of the equation. Furthermore, if you want to find the value of the foci, you would get almost Pythagorean about it. You're going to take your smaller denominator, square it, and set it equal to the difference of the larger denominator minus the square of the value of the foci. Okay, and again, this is if you're we always are starting off with being centered at 0, 0, but then we can complicate matters by being centered elsewhere. So if you were centered elsewhere and you want to take that information about foci, vertices, and the structure of the equation, you're going to look at table 3. Again, they say don't memorize this, just use some transformations. Hey, you do you. If you want to memorize this table, if that's the best way according to your learning style to really internalize this information, by all means do it. So here is a wide and a tall example of these two ellipses. And so notice with the wide one, again, the squared value, the denominator is larger for the squared x than the squared y denominator, and it's reverse if you have a tall one. Okay, so these are the things that help me get to know all of this information. Let's go through some examples and get to know what it means to draw and come up with equations for ellipses, or just to recognize them. And that's what the purpose of this first exercise is. Let's look at some figures, numbers 13 through 16, there's 4 of them, and match them up with their corresponding equations. Okay, looking at number 13 first, notice we've got a wide one. It's wide. For instance, we're going to have the x denominator is going to be larger, okay, and the width from where it's centered at the origin, and all these are going to be centered at the origin, by the way. That's the one thing that's common among all 4 of these. The distance from the origin to the vertex is going to be 4, okay, so we'll keep that in mind. And so this one's looking like a good candidate, right? But let's see, that's not the one that we want because we'll notice that the height of it, so we have a major axis, what do we call this? Yeah, a major axis distance is 8. So excuse me. So we're going to divide that by 2 and then square it. So we're going to get that the denominator for the major axis needs to be 16, and then the height is 2 here, 2 here, so that's a total of 4. So we'll divide that by 2 and then square it and get 4. So believe it or not, C is the best value for that one. It wouldn't be A, because if we had A, then that means it'd be having a width of 2 and a height of 1 on each side, on the other side of the vertex. Or excuse me, not the vertex, the center is the correct word there. Okay, not sure if that was terribly helpful. Let me put my notes on it. The x denominator we know is bigger. Because it's wide, and the width is going to be going from -4 to 4. So basically you take this number and you square it, and that gives you the value underneath the x squared denominator, and then the y squared denominator, it goes from -2 to 2. So basically you take this number and you square it, and that gives you that denominator of 4. Okay, so that's why we're getting C here. Now for number 14, we have the major axis going the other way, so this is a tall. So basically it's going to be the y squared is going to be like for all of these same numbers, but it's going to be the y squared, so that means this next one is going to be D. Okay, And then this one's going to be tall, but it's only going 4 and then 1 for the denominators, the 4 being underneath the y squared, so that means this one's going to be associated with b. This one being wide, it's going to be squared, and or excuse me, the larger one's going to be associated with the x squared term. So that means it's going to, I mean, process of elimination, we could say a, but it's going to have a 4 by 1 situation where the 4 is with the x squared term. So that's looking like A. Okay, cool. So sometimes my terminology and descriptions of this are not conventional, and so hopefully it's helpful, but if it's not, we can in class go towards more traditional elements there. Okay, let's dive into our first example. We're going to analyze this equation, find the center, vertices, foci of each ellipse, and then graph it. Okay, so we know by virtue of having no transformations here on the x and the y directly that we are centered at 0, 0. Okay. Furthermore, we will notice that the major axis is parallel to the x-axis because the larger of the two denominators is with the x squared term. So it's parallel to x-axis major axis, that is. It's so wide, therefore, is basically the way that I describe it, okay? Furthermore, we get to say that a squared equals 9, okay? B squared equals 4. So what, therefore, is the value of the foci? Well, we can use these values to calculate the foci by saying b squared equals a squared minus c squared. Okay, so then that means we'll have a 4 here, 9 there, c squared. So that means c squared has to equal 5, and therefore c has to equal root 5. Okay, cool. So then the foci, therefore, are h plus or minus c, comma, k, which for this case, because h and k are both 0, we will have plus or minus root 5, comma 0. So root 5, 0, and negative root 5, 0. Those are your foci. Your vertices are h plus or minus a, comma, k, which will be a is going to be 3, because you'll take the principal square root of a squared equaling 9. So that'll be 3, 0, negative 3, 0. Okay, so we could plot all of those elements, and we're going to draw, yeah, all the way around. Okay, so also, what do we want to say? So yeah, we know that the width of this wide ellipse is going to be 3 on each side, so it's going to have a width of 6, and the fact that the b squared value is 4 means it's going to have a height of 2 on top and 2 on bottom, so a total height of 4, so to speak. Okay, so let me go ahead and reveal that, and all of the things will come into play there. Okay, so yes, notice that we have our ellipse, we have our vertices here at negative 3 and positive 3, and then these green dots are the locations of the foci. So that's negative root 5 here, root 5 there, in those 2 positions. And then yes, make sure that your heights are correct here by taking into account your b value being, b squared being 4, so that means the b is 2, positive and negative 2. Okay, cool. Moving on. Number 22. Aha! Now notice that this equation is not in a very friendly format, so what we need to do is force this constant term on the right-hand side of the equation to be a 1. So basically divide the whole thing by 18. So we'll get x squared over 18 equal, or plus y squared over 2 equals 1. Now, we can say that definitively, I mean, we could have said it earlier too, that our center, excuse me, let's do center, is at 0, 0. That's your h and your k values. Okay. Furthermore, your a value is going to be a squared, excuse me, is 18. B squared equals 2. So we'll be able to calculate C from there. Furthermore, the fact that the x squared had the larger denominator means that we have another wide one. So it's going to be wide. So it's going to be parallel to the x-axis, what do we call it? Major axis, that is. Okay, so it's going to be a wide one. Boop. Furthermore, what's the C value going to be? Well, remember, a squared minus c squared gives you b squared. So we have 18 minus c squared equals 2. So that means that c squared has to equal 16. So c equals 4. Okay, so we know from there that the foci are, remember, it's h plus or minus c comma k, which is 4, 0, negative 4, 0. The vertices are h plus or minus a comma k, which is going to be 3 root 2, 0, negative 3 root 2, 0. Okay, so plotting all of those things on the axes here, and also noticing that the, I mean, so obviously it's 3 root 2 in width, which is, you know, somewhere between 4 and 5 on either side. But then what's the height going to be? The height is going to be square root of 2 on either side. So even though it's wide and we want to know that stuff, we also want to know when are we crossing the y-axis on top and bottom, and that'll be at square root of 2. So square root of 2 is like, you know, a little bit less than 1.5, so that's why we have those there. And then yes, notice that the foci in green are incredibly close to the vertices in blue. Okay, yes. Great, moving on. All right, let's go ahead and find the equation of the ellipse and then graph on the coordinate plane provided. Starting with number 2, we have foci at 0 plus or minus 2. So this right here will tell us the value of C, right? So C equals 2. And furthermore, we know that we have to be centered at 0, 0 if this is the structure of our foci, if we don't have any h value. And we're surmising from this that our c value is straight up 2. So then hk equals 0, 0. And the length of the major axis is 8. So that means that a has to equal 4. And so a squared equals 16. And then, and so, and also, furthermore, since the foci are 0 plus or minus 2, that tells us that we are parallel to the y-axis. So we're actually going to be, this one tells us that we're tall. Parallel to y-axis. And the fact that the major axis is 8, so that tells us that we're going to be having the larger squared value under the y this time. So our structure is going to look like this. Okay, and we have A and we have C, so we can use that to calculate B. We don't yet have that. So remember, B squared equals A squared minus C squared. So that means that we have 16 minus 4. So B squared therefore equals 12. So that'll be what we put underneath this right here. Oh, sorry, that's supposed to be an H. I didn't mean to put a B up there. That's not what we wanted. Let's see how long this takes to erase. Okay, not bad this time. H is what I meant to put there. Okay, but the H and the K are 0, so it's like, you know, not a very important thing. We'll have x squared over 12 plus y squared over 16 equals 1. All right, and what does that look like in the picture form? Well, okay, so we know that the foci, yep, that was given to us. So the vertices are at positive and negative 2 root 3. Oh, excuse me, that's not true. Positive and negative 4 on the y-axis. Yep, because that's our A is 4. So vertices are therefore 0, 4, and 0, negative 4. Okay, let's reveal the figure here. Indeed. So there's our vertices, our foci here in green, and the width of our tall, you know, it's just barely tall, it's just barely taller than it is wide, is going to be at square root of 12, right, for either side, aka 2 root 3, 2 root 3. Cool. So there you have it. Cool. Let's do this again, but this time we're given vertices at plus or minus 5 and 0, and a C equals 2. So how do we use this information in order to come up with the equation of the line? Again, we know that we're centered at 0, 0, because otherwise we wouldn't have this 0 value as part of our vertices. And we know that, so okay, C equals 2, that's all great. Center is at 0, 0, so that's your H and K values. And then we know that we are, because our vertices being having values in the x position rather than 0, we know that we are wide, okay? So that tells us A equals 5, so A squared equals 25. B squared equals A squared minus C squared, right? It's supposed to be an equal sign. So that means that B squared equals 25 minus 4, because C was a 2. So that means B squared equals 21. So B equals root 21. Great. Do we need any more information than that? We need foci. Foci are going to be at 2, 0, and negative 2, 0, because the C value was given to us. So that was quick and easy. Furthermore, okay, so we know that the A value, right, is, okay, so we're going to have that structure of x minus h squared over A squared plus y minus k squared over B squared equals 1. But remember, h and k are 0. A squared equals 25, B squared equals 21. So we'll have x squared over 25 plus y squared over 21 equals 1 as the equation that we want. And then here we go. Well, let's go ahead and graph that. Okay, so we'll notice that we have the vertices at plus or minus 5. That's the blue dots here. The green dot locations are the foci that we got from the C value. And the height of the places where we intersect at the y-axis are going to be that square root of plus or minus square root of 21, that b value. All right, cool. So there we go. Let's move on to number 40, where we write the equation for this given ellipse. Notice that the center is at -1, -1, so that means hk equals -1, -1. Okay. Furthermore, it has, now it's not explicitly shown, but it's really up against the value 0, -1 is on the ellipse. And it's long, or tall rather. It's tall, not wide. So that means that its length from here to here is 2, right? So that means that the a value is 2. So therefore a squared equals 4. And furthermore, it has a width of just 1 in this direction, so that means the b value equals 1, b squared equals 1. Nothing earth-shattering there. So we have enough information to bust out the equation of the line. Being that it's tall, we know that we have the form x minus h quantity squared over b squared, right? Plus x minus, or y minus k rather, sorry, y minus k quantity squared over a squared equaling 1. So give that its final form, it'll be x plus 1, because remember h is -1 over 1, so just nothing at all. Actually, I don't even need that horizontal line, do I? I just need to square it. Plus y plus 1 squared over 4 equals 1. And that'll be the final form of the equation of the ellipse that we were tasked to find. Okay, just a few more examples. I swear we're done pretty soon. I just wanted to definitely do one of this ilk because it requires that you complete the square in x, okay? Maybe rearrange the terms to kind of highlight this. 9x squared minus 18x plus y squared equals 0, and say to yourself, all right, I got to focus on this bit. But, in completing the square for x, I'm going to have to get rid of that coefficient. So divide both sides by 9, and you'll get x squared minus 2x plus y squared over 9 equals 0. Why isn't the left-hand side changed? Well, divide 0 by 9, and what do you get? Still 0. Okay? So now we're going to complete the square in x, and that'll entail awesomely just adding a 1, and thank goodness that does a nice thing on the side as well, because 0 plus 1 is going to give you that 1. So here's me adding the 1 to both sides, and that'll complete the square on x. So that'll be x minus 1 quantity squared plus y squared over 9 equals a 1. Cool. We have a, which equals a 3, because a squared equals 9 there, right? B equals 1 by virtue of having no denominator here on the x squared term. Furthermore, h, it looks like, equals a 1, k equals 0. And we can get c in order to find the foci by taking b squared equals a squared minus c squared. And what do we get there? Well, b is a 1, a squared is a 9. So that means that we've got c squared equals 8, which means c equals 2 root 2. So we have a center at center 1, 0. We have a foci at and now that'll be at h comma k plus or minus c. Now why do we know that? Because by virtue of having the larger of the two denominators associated with the y squared term, that means that we're parallel to the y-axis, so we're going to have a tall, right? We know that the form of the foci will take on h comma k plus or minus c, so that'll be 1 comma 2 root 2, 1 comma negative 2 root 2 for the foci. The vertices will be at h comma k plus or minus a, which will be 1 comma 3 and 1 comma negative 3. Okay, so put all of this information together and boop, here we go. So again, just to be clear, the vertices are at 1, 3, 1, negative 3. That's the blue dots there. The foci are at 2 root 2 and negative 2 root 2, also going through x equals 1. The center is at 1, 0. That's the purple dot there. And the width of this tall parabola, or excuse me, tall ellipse, is got to be 1, because there is no, trivial, or there's only the trivial denominator for the x squared term. Okay, so you just draw the red trajectory all around those elements and you have your ellipse. Okay, let's do 2 more. Okay, here's number 60, where we have vertices and a c value. And how do we take all that information in? Well, we got to find the equation of the ellipse and then graph it. So we know that since the vertices have the same x values, that we're going to be parallel to the y-axis. So we're going to be tall, okay? Tall. So that tells me quite a bit right there. So my foci, oh, excuse me, and the length of the major axis, since the distance between the 5 and the negative 1, so length of major axis is 6. And so that tells me that my a value is a 3, okay? And since I'm tall, I'm going to be having my larger denominator under the y squared term, okay? Furthermore, my c is 2, good to know. So b squared equals a squared minus c squared. I'll use that to calculate my b squared, and therefore my b. So that'll be 9 minus 4. So b is basically root 5. B squared is 5, so b has to equal root 5. Okay, so my center, so since I have 2, 5, and 2, negative 1, I know that my 5 has to equal, this 5 bit right here, has to equal k plus a, right? And that negative 1 has to equal k minus a. So that means, since my a value is 3, that tells me that k has to equal 2. So then I take my that information and I calculate my foci, which are h comma k plus or minus c. I have, oh, do I have my h value? I do not have my h value yet, so let's calculate h by saying that, oh, well, here we go. The vertices have to be in line with your h value, so that means that right off the bat, that tells us that h equals 2. Okay, so the foci therefore being h comma k plus or minus c, my foci are 2 comma 4, 2 comma 0. My vertices were given. My center therefore is 2, 2. Center 2, 2. Okay, and I think I have all the information I need to get my equation and also graph. So I know that since I am a tall ellipse, I am going to have my larger squared value denominator underneath my y squared term. So that'll be x minus 2 all over 5 squared plus y minus 2 all over 9 squared will equal 1. So there's the equation of the line. And then here is all of those elements getting put together to make my ellipse. Vertex as given was 2, 5, and 2, -1. There they are in blue. My foci were at 2, 4, 2, 0 in green. My center was calculated to be 2, 2 in purple. And I know that the width of my tall ellipse has to be √5 and √5. So that'll determine how wide these guys are. So for the distance from the purple to this part of the red trajectory is going to be √5, if I'm not mistaken. Okay, last one, and then I will turn it loose to classroom discussion. We are centered at, here we go. 1, 2, vertex at 4, 2, contains the point 1, 5. Okay, so this tells us that since the vertex and the center both have values of 2, that we are parallel to the x-axis. So we're going to be a probably wide one, okay? So parallel to x-axis. A therefore is going to be 3 because that's the distance from the center to the vertex in the x's, and the other vertex has to be the same distance away, so that means other vertex is at -2, 2. Okay, because that's going to give me the other side of the center. Okay, and it contains 1, 5. So in order to find the value of b, so we have a, and we need to find b and then also find c, but we'll find the value of b first by taking the center value and the a value and plugging that in. So, and by virtue of assuming that we are parallel to the x-axis, we will say that the x squared term is going to have the bigger. So we're going to go for this structure. And we're going to plug in what we know, okay? H is a 1. And a squared is going to be 9 plus y. K is 2. We don't know b squared, we're going to solve for b squared, okay? By plugging in, 1, 5. Plug in. So that'll be 1 minus 1 squared over 9 plus 5 minus 2 squared over b squared is supposed to equal 1. So this zeroes out. You guys see that? Because 1 minus 1 is 0. Bye-bye. And so then we're just left with 3 squared over b squared equals 1. Well, then therefore b has to equal 3, right? Okay, well if b equals 3 and a equals 3, interesting. So now we can write the equation of the ellipse, and it's going to look like this. Oops. It's supposed to be parentheses. Let me erase this little guy right here. Try that one more time. That'll be y minus 2 all over 9 equaling 1 squared. Okay, so notice that the a squared and b squared values are the same. Whenever that happens, you're not actually looking at an ellipse, you're looking at a circle. Boom, yep. So here is the point 1, 5 that we were told was on the supposed ellipse, and the center we determined was, or no, we were given that it was 1, 2, and one of the vertices was 4, 2, that's this one right here, and we used that fact to find the other vertex of -2, -2, and then everything else fell into place. This additional point was exactly above the center and exactly as far away as the other two vertices, so they act as more vertices. In fact, every point on this outer edge is a vertex. It's exactly the same distance around. So that means that the C value is 0. So the foci, is actually just melds together into one center. The center is the two foci, essentially. Okay. Whew, my goodness. So I'm sure you have more questions. Let's let them rip when we see each other in class. See you soon.